Okay, good morning. What happened to the participants today? I'm seeing only 9 people. Any particular reason why nobody is here?
We just wrote a quiz, ma'am. So they might be taking
Oh,
some.
okay. Fine then. I'll start because it's already time. So last time I was talking about lossy dielectric. I said that is going to be the most general case. So how wave propagates in a lossy medium. That's what we are going to see. So in that context, what happened was we discussed what is a lossy medium, and we have seen that conductivity is small but not equal to 0. Then after that, we used the 4 Maxwell's equations in the phasor form, and I showed you how it becomes the phasor form also. And using these equations, we arrived at what is called the Helmholtz equation. Two Helmholtz equation we had, equation 2a and 2b. Okay, and after that, what we have seen is because gamma square is a complex quantity, okay, gamma also should be a complex quantity. Therefore, we wrote it as some alpha plus j beta. And ultimately, what we have done before leaving yesterday was arriving at equation 3 and equation 4. Equation 3 is alpha square minus beta, or sorry, beta square minus alpha square, and alpha 4 is beta square plus alpha square. So you know that using equation 3 and 4, you can eliminate either beta or alpha and find out alpha beta. Okay, this is simple mathematics, and you have arrived at equation 5 and 6. So equation 5 is beta and equation 6 is alpha. And if you see here, I told you definitely some what is common between the two of them, you can see omega is there, and then under root mu epsilon, then again one under root of 1 plus sigma by omega epsilon. This sigma by omega epsilon, does it remind you of something? Sigma by omega epsilon, does it remind you of something?
Speed of light, no.
Now, ratio of displacement current density and conduction current density, do you remember? Not able to remember? You had seen this equation in the previous chapter. Okay, this equation was the ratio of the displacement current density and the conduction current density, the sigma by omega epsilon. So using this, you have to remember. Okay, and another difference is that in beta there is a +1 figuring, and please remember this +1 that you're seeing here is not part of the under root. It is not part of the under root inside. And similarly, you have a -1 here. You keep doing problems again and again. This equation is not difficult to understand, okay, or to remember. Now, what we will do is we will apply this to a particular situation. So what is the situation we are taking? We'll consider a wave. Okay, let us consider a wave. Okay, a wave that is propagating along the plus z. Remember, it is propagating along the plus z direction, but the electric field itself is going to have only the x component. It is going to have only the x component. Okay, we are going to write our Helmholtz equation for this particular wave. The wave is traveling along the plus z direction, but the component of electric field is only the x component. Okay, or if I have to write it in the phasor form, I will write Es is equal to Exs function of z. Why x is coming here? X is coming here because there is only x component, and z is there because it is a function of z. This I have been telling you from last chapter. Okay, so now we will put it into our Helmholtz equation. When you put it into your Helmholtz equation, what happens is normally Helmholtz equation, you know, is del square. Helmholtz equation is del square, okay, E Es minus gamma square Es equal to 0. And you know what is del square? Del square, you know is dou square. It is dou square by dou x square, dou square by dou y square, dou square by dou z square, right? You can see that since your electric field is a function of, it's a function of Z. It's a function of Z only. This and this will go. So you're left with only dou square by dou Z square. So that's the reason why we are writing dou square by dou Z square. And then of course minus gamma square EXZ is going to be equal to 0. Now you have to get the solution for this. Okay, now you know that the solution, what is solution? Solution is getting what is E. Okay, so when you get the solution, look at this. You are going to get a general solution. And you can see from this equation that definitely the solution will have an exponential form. You have seen these kind of equations even in physics. Okay, the solution for this equation has to be an exponential equation. Okay, and you will get two particular equations, one written in red and the other written in blue. You can see here two particular solutions you will get. And look at the form of the equation, E naught e to the power of minus gamma z, and in other case it is e to the power of plus gamma z. Here it is E naught, here it is E naught prime. Okay, and what is this red part? What does this first part actually represent? The first part represents a wave traveling along the plus z direction. It is a wave traveling along plus z direction. How do I know it is plus z? Because there is a minus coming here. Therefore, it is along the plus z direction. And what is the other part? The other part is a wave traveling along the minus z direction. So you're getting you're getting two particular solutions. One, talking about an electric field where the wave is traveling along the plus z direction. Another where the wave is traveling along the minus z direction. A linear combination of both these will give you the general solution. Okay, like for example, if I'm talking of a standing wave, both are going to be non-zero. Okay, so but in our case, what did we start with? We talked about a wave that is traveling only along the plus z direction, only along the plus z direction. So as a consequence, what happens is the second part will automatically become zero. The second part will automatically become zero. How will the second part automatically become zero? The second part will automatically become zero if this coefficients become zero. Okay, therefore, you're just left with Exs as a function of Z is going to be equal to E naught e to the power of minus gamma Z. Only this is left. Okay, so next what we do is let us take that. Okay, and this is the phasor part. This is the phasor part. So now let us write the harmonic form of the electric field. When you're writing the harmonic form, this is a cosine. I told you we have to take the real part. Okay, so you will write the real part of the phasor and e to the power of j omega t. And of course, this ax cap is coming because that is the direction of the electric field. Okay, so now let us look at that. So this is going to be real part of what is EXS? EXS is E naught e to the power of minus gamma z. Just now we wrote. And then of course e to the power of j omega t is there. Now what we will do is look at the next step. Real part of E naught. And do you remember what is your gamma? Gamma was equal to alpha plus j beta. Gamma was equal to alpha plus j beta. So let's use that here. So when you use that here, what happens? You get E naught. Then you get e to the power of minus alpha z. Okay, then you get e to the power of minus j beta z. Why this minus j beta z? Minus j beta z is coming because there is a minus here. Okay, because there is a minus here. So minus gamma will be minus alpha and you're getting minus alpha minus j beta. Did you get this step? In this step, there was a minus gamma, minus e to the power of minus gamma z. Instead of minus gamma, you're going to put minus alpha minus j beta. And then you know that exponential of a plus b is exponential of a into exponential of b, product of two exponentials. So that's what has been done here. You're writing it as a product of two exponentials. And then of course, e to the power of j omega t is going to be there. Now what we will do is, J is there only for these two terms. J is there only for these two terms. So let's just combine these two. So what will you get? You get real part of E naught. e to the power of minus alpha z, and then combining these two, you will get e to the power of j omega t minus beta z. Okay? Or what is the real part of an exponential? Real part of an exponential, if there is a j, real part of e to the power of j theta is equal to cos theta plus j sine theta. I'm just using this. Okay, if I use this for this part, okay, real part will be just a cosine function. It will be just a cosine function, cosine of this phase. Okay, therefore, and but the rest of it will remain as it is. Okay, because exponential of a real number will not change because it's already real. So real part is just that only. Therefore, e to the power of minus alpha z remains as it is, e naught remains as it is, but you get cos of omega t minus beta z. Of course, the direction of the electric field we already said is along the x direction. So this equation 7 represents the equation representing the electric field of this wave. Okay, so this is the equation representing the wave, the electric field of the moving wave. And where is it moving? It is moving in the lossy medium. And can you just look at this and compare with what you have seen in the last chapter? In the last chapter, when we wrote the electric field, one of the forms of electric field that we wrote was E of ZT is equal to E naught, then cos of omega t minus beta z, and it is along the x direction, for example. Okay, what is different between this and equation 7? Anyone? What is the difference between the equation that you wrote in chapter 9 and this one? Anyone is able to see the difference?
New one is exponential.
Can you speak loudly?
New one is exponential, ma'am.
What is that?
New one is exponential.
Yeah, the new one is this part. You are having a new part there. So it is exponential, and look at the minus sign. There is an exponential with a minus sign, and it involves alpha, and it is a function of z. So that means as z keeps increasing, as the wave keeps moving along the z direction, what is going to happen to e to the power of minus alpha z? E to the power of minus alpha z will become smaller and smaller. Isn't it? It's an exponentially decreasing function. Or if I'm going to plot, let me just, maybe I'll go to the next page and do that. Yeah, it's already there. It's already there. So if I plot a function, which is, let us say, if I'm going to plot a function of z, which is e to the power of minus alpha z, okay, and I'm plotting it as a function of z, how will it look? How will it look? It will be exponentially falling. Yes or no? Are you realizing that it's exponentially falling with z? It will have maximum value for z equal to 0, and z keeps increasing. The e to the power of minus alpha z will keep falling exponentially. So now with this, you look at this equation. Now look at this equation. E of z comma t is equal to E naught e to the power of minus alpha z cosine of omega t minus beta z a x cap. So what does this mean? This means that when a wave, look at this figure, I have already shown the plot. When a wave is moving along the z direction, okay, and what is this medium? That means a wave is entering into a lossy medium. When it is entering into a lossy medium, let us say that initially, if it is having an electric field of this value, if the electric field is this much, my God, my pen is not, my pad is not aligned properly. Okay, if this is my electric field initially at z equal to 0, when it travels at distance z, what is going to happen to the electric field value? And please remember, electric field is a cosine function. So as the wave travels, the electric field value will keep changing in a cosine fraction. It will keep changing in a cosine fraction. Okay, but then if this e to the power of minus alpha z was not there, then what would have happened is, the wave would have kept on going like this. The electric field would have kept on going like this. The maximum value every time would have been only E naught, even though the wave kept moving. Okay, but now what is happening? Now what is happening? The maximum value is not going to remain E. It is going to be E naught e to the power of minus alpha z. Or when you draw the cosine function, you're finding that the amplitude of the wave is decreasing as a function of z. Or what is happening in this case is called attenuation. Yesterday I used the word attenuation. Okay, so what is happening here is attenuation. Attenuation means losing. So what is getting lost? What is getting lost is the amplitude of the electric field. Whenever you're talking about an electromagnetic field, you talk about amplitude of the wave. Any wave will have an amplitude. But we talk about always the amplitude of the wave as the electric field. It is the electric field that is changing as a function of time and in a cosine fashion. Of course, perpendicular to that, you have the magnetic field. Normally, we like try to write in terms of electric field. Okay, or you can come to the conclusion that when a wave propagates through a lossy medium, now you are understanding why it is called a lossy medium. When a wave propagates through a lossy medium, the amplitude of the wave decreases exponentially with distance traveled. Exponentially with distance traveled. Now let me ask you one question. Let me just ask you one question. If I have two waves, one with alpha 1 and another with alpha 2, or let me talk about two different mediums, not the same, not the wave. If I'm talking of two different mediums, one having alpha 1 and the other having alpha 2, and alpha 1 is greater than alpha 2. Alpha 1 is greater than alpha 2. How do you think the falling will be happening? In which case will the fall be faster? In which case is the attenuation going to be happening faster?
Alpha 2, ma'am.
Alpha 1 is greater than alpha 2. Look at this.
Alpha 1 only.
Alpha 1 is greater than alpha 2. So you put here alpha 1 and C, then you put alpha 2 and C. In which case is the fall?
Higher rate it will fall.
Yeah, so larger the alpha 2, faster will be the fall. So if I have to show it here, I may show like this in that, but in the case of alpha 2, it will be like this. These are the concepts that you should understand. So that means the attenuation of a wave is going to depend on the
Ma'am, it will
distance
be opposite,
traveled.
ma'am.
Huh?
Alpha 1 will fall faster.
Which one?
Alpha 1 will
Oh,
fall
sorry.
faster.
Oh, I am one second. Alpha 1 will fall faster. Sorry. Or instead of changing everything, I'll just put alpha 1 less than alpha 2. That will be easier. If alpha 1 is less than alpha 2, then it takes more time to attenuate. It can travel through a larger Z before attenuation. Whereas in this case, for a smaller Z itself, that much attenuation will happen. Does all this remind you of something that you studied in your past? In your previous Janma, you studied something. Damped oscillation. Do you remember? Ben?
Yes, ma'am, I do.
You remember that? Okay. So there also we talked about something called a damping factor. There what was damping? The damping was the displacement of the wire or displacement of the string. Same concept. So here what is happening? It is the displacement of the electric field. It is the electric field that is getting damped. Okay, same ideas. Okay, so now, so that means this alpha is having some significance. Let's see what that alpha is. Similarly, let us, if we start with the other Helmholtz equation, if you had started with the Helmholtz equation involving the magnetic field, then also you would have arrived at a similar equation. A real part of h naught e to the power of minus alpha z e to the power of minus j omega t minus beta z a y. Okay. Yeah, you would have arrived at a similar equation. But now there is something different here. Instead of an E naught, you are going to have an H naught. Because this is H. So you will have H naught. H naught will be the amplitude when Z equal to 0. Okay. And there is now a relationship between H naught and E naught. I kept telling you from the beginning, H naught and E naught are related because we are talking of dynamics, they are related. So now we come across that relation. The relationship between the amplitude of the magnetic component and the electric component is given by H naught equal to E naught by eta. This is called eta. The symbol is called eta. It is H naught equal to E naught by eta. And what is eta? Eta is called the intrinsic impedance. You know what is impedance, right? Impedance, you know what is a unit, ohm. Okay, so this is called intrinsic impedance. It is called intrinsic impedance because impedance is resistance, right? This is called intrinsic impedance because it is actually the property, it's an intrinsic property of the medium which talks about the resistance of the medium to your wave. Which talks about the resistance of the medium to the wave. That's why it's called the intrinsic impedance. Okay. Now, another thing that I should immediately point out here is in the last chapter, I kept on talking about the relation between the direction of the electric field, the magnetic field, and the direction of propagation. If you remember this equation, we will use that also here. And see that it is according to this equation that you have got the magnetic field direction. Look at the magnetic field component direction. It is along the y direction. Whereas your electric field was along the z direction. And propagation is along the positive, sorry. And the magnetic field is along the y direction. Electric field is along the x direction. And the propagation is along the positive z direction. All the three are mutually perpendicular to each other. So maybe I'll just write it here and show you that it is consistent. So AE is along A x cap. Then AH is along AY cap. So what is the direction you should get? AZ cap. So it's fine. Okay, so every time do this check. And next, I just told you about intrinsic impedance. Even now I've not talked about what is alpha. Okay, I'm just keeping it there. But you know that alpha is somebody important. So what he is, we'll see. Now let us talk about intrinsic impedance. So intrinsic impedance, that is again, it is an impedance. It's a property of the medium. So intrinsic impedance is given by this particular formula, J omega mu by sigma plus J omega epsilon. Okay, or you can see that you can write it as a real part. You can talk about the real part of the comp or the magnitude, and you can talk about an angular part. You can talk about a real part and you can talk about an angular part. Okay, now this real part is given by the expression under root of mu by epsilon divided by 1 plus sigma by omega epsilon square, the entire thing 1 by 4, to the power 1 by 4. And this theta eta is also significant. This theta eta is actually related to, this theta eta is the angular part of the intrinsic impedance, and tan of 2 theta eta is sigma by omega epsilon. Now the sigma by omega epsilon is going to follow you all the time. Remember sigma by omega epsilon was also there in the alpha equation and the beta equation. And I told you it's a ratio of the displacement current density and the conduction current density. So the sigma, so it's not going to be difficult to remember because you are going to again and again keep seeing this fellow. Okay, and it is related to the angular part of the intrinsic impedance. Now I'm sure there are one or two at least here who will ask, man, are we supposed to remember this? Yes, you're supposed to remember this. The author expects you to, he directly gives you this result. He directly gives you this result, but I have actually worked it out. But then it's a long material. Okay, so I don't want to share it as a slide. It's a long material. I don't want to share it as a slide. Okay, it's a handwritten material. Okay, I will call it Appendix A. Okay, I will call it Appendix A, and it gives you details on how this equation 10, 11, and 12 have been arrived at. It is not required for the examination. It is for the curious minds. I've only kept it for the curious minds. For those curious people, I will share it. If you want, you can just go through it once. Okay, but the author also doesn't even give this appendix. He doesn't even give this appendix. He is directly giving you the result and expecting that you should know this result and use this. Is that clear? Okay. Now what we'll do is let us, so what was our equation? Let me just write here. Our equation just that we got was, instead of E naught by, so what did we write sometime back? We wrote H naught equal to E naught by eta. So that's what we have seen, where eta is called the intrinsic impedance. Now what we will do is we will write H naught equal to E naught divided by eta itself is having two components. Okay, so one is the magnitude and the other is going to be J theta eta. So put both of them. Put both of them there. After you're putting both of them there, what you can do is apply this real part. Apply this real part to this. When you apply this real part to this, what will you get? You will get, when I apply the real part, what I will get is E naught divided by modulus of eta will not change because it's anywhere real. But here, real part of e to the power of j theta eta will become what? What will it become? Cosine. Right? It will become cosine. So what I will now do is I will not touch that step right now. I will not touch that step right now. I will simply do another thing. What I will do is let me write the equation for H. H is going to be, okay, real part of, I'm starting from here, real part of E naught by modulus eta. And what I will do here is e to the power of minus alpha z, let me write, and I will combine it with this e to the power of j theta eta. Let me combine with this. Let me combine with this. When I combine with this, what I will get? I will get minus j omega t, then minus beta z, and I will get from the denominator, when it goes to the top, it becomes minus j theta eta. So therefore, it becomes minus theta eta. Did you understand this step? Revant?
Ma'am,
Did you understand the step?
not quite, ma'am.
Quite. Okay. You see here. Nothing, yeah. I have put the modulus of eta, then I have put e to the power of j theta eta. Right? Did you understand that? Did you understand this result? This is the result that I have given. You are supposed to take it for granted. H naught is equal to E naught by eta. And I have shown you that eta is having two parts, modulus eta and e to the power of j theta eta. Okay. Now, e to the power of j theta eta, I can actually club with this fellow, no?
Okay, ma'am.
When I club there, what will happen? I will get minus j omega t minus beta
Minus
z.
theta.
Yeah. So it goes, and of course, there it will be actually minus theta. Okay. So I will get this. Now I'm going to apply this real. Now I'm going to apply this real part. So when I apply real part, what happens? All this will remain as it is, but this exponential of minus j will become cosine. It will become cosine. So I will get cosine of omega t minus beta z minus theta eta.
Okay, ma'am.
Minus theta eta. Direction is ay. And then what is happening to H naught? H naught is now, okay, my God, my orientation of the pen. Okay. So what are you going to get? You're going to get E naught by modulus eta will become H naught magnitude, and then you have your exponential part, and then cosine of omega t minus beta z minus theta eta. What does this mean? What does this mean? Compare this equation and equation 7. Equation 7 I purposely wrote here for you to compare. So what is the difference between both of them? Both are perpendicular to each other. Yes, you know. Both are having the same form, cosine, cosine. Omega t minus beta z is the same. Yes. Then e to the power of minus alpha z is also there. But something else is changing when compared to what you saw in the last chapter. What is that? There is a phase difference. There is a phase difference between the electric field and the magnetic field. And when does this happen? This happens whenever a wave is going to travel through a lossy medium. And what is going to be that phase difference? The phase difference is going to be theta eta. Okay, so you conclude that when a wave propagates, so we are now combining all the things we have seen today. When you combine everything that you have seen today, you come to a few conclusions. What is the first conclusion? When the wave propagates through a lossy dielectric, it attenuates. So that's the first thing you see. It will attenuate. So as a result, the amplitude falls off as e to the power of minus alpha z. Okay, and what is this alpha now called? It is connected with attenuation. So this alpha is now having a physical significance. This alpha is having a physical significance. This alpha is called the attenuation constant or the attenuation coefficient of the medium. It is a property of the medium and it is called the attenuation constant or attenuation coefficient of the medium. So that tells you how much of attenuation will happen when a wave propagates through the lossy medium. So this is the first result. Then other than that, there is also one more result you are seeing. What is that next result you are seeing? The next result is that there is a phase difference between, otherwise normally in an electric field, in a EM wave, what will happen is, if I have to show an EM wave, how I will show it in a normal free spaces, it will be like this. Let us say this is the direction of propagation. Then I will show you the electric field. The electric field will be perpendicular like this, okay? And if you show the magnetic field will be perpendicular to both of them and you can show it in a different plane like this, okay? So I'm showing actually the electric field is in one direction. What is my, okay. So the electric field is going to be in this direction, magnetic field is perpendicular and propagation is perpendicular. Are you able to see this? Okay, and you will see that whenever E becomes 0, B will become 0. They will be in phase. Whenever E becomes a maximum in that curve, the B will become maximum. They will be in phase. But then when it is passing through a lossy media, it is not going to be in phase. There will be a phase difference. A phase difference is theta, eta. Okay? And the significance of alpha, I just told you, it is the attenuation constant. It is a measure of the spatial decay of the wave. It's a measure of the spatial rate of decay of the wave when it is passing through the medium. And what is a unit? Alpha is measured in terms of Napers per meter or capital NP by meter, or you can also write it in terms of dB per meter. Okay, now let us see what is the significance of 1 Napier. Okay, what is the significance of 1 Napier? 1 Napier is, we said the attenuation is e to the power of minus alpha z. Okay, when z becomes equal to alpha, what happens? When z becomes equal to 1 by alpha, when z becomes equal to 1 by alpha, what will happen? The attenuation part will become e to the power of minus 1. Yes or no? Guys, E equal to E naught e to the power of minus alpha z into cosine of the rest. Okay, and it is along the ax cap direction, let us say. Okay, now look at this part. What will happen to the amplitude when z becomes equal to 1 by alpha? When z becomes 1 by alpha, I will get E naught e to the power of minus 1 into cosine of the rest of the things will be there. Okay, so now I can actually tell you what is the significance of this alpha being equal to 1. Alpha being 1 simply means that the amplitude has reduced to 1 by E of the initial value. It just means it reduces to 1 by E of the initial value. Okay, and what is beta? Beta, you are having cos of, you had that cos of beta z minus omega t, or was it omega t minus beta z? Yeah, you had cos of omega t minus beta z. Omega t minus beta z. So what is this beta? You remember gamma is equal to alpha plus beta. So what is this beta? Beta is called the phase shift per unit length. It is given in radians per meter that we have seen in the previous chapter also. And it has got another name. It is called phase constant or wave number. Beta is called wave number k, or it is called phase constant, or it is called phase shift per unit length. And beta is given by the equation beta equal to 2 pi by lambda. And the propagation velocity is given by omega by beta. This, you know, omega by k, you have studied in physics. So propagation, the velocity is omega by beta, and which will be 1 by under root of mu epsilon. I put all this in the beginning of the chapter. These are preliminary things that you are supposed to know. Okay, now let us come to the second result you have seen today. When a plane wave propagates through a lossy medium, it suffers attenuation, and additionally, the electric field and magnetic field are out of phase by theta eta. And this is because of the intrinsic impedance of the medium. And which is leading? Electric field will always lead the magnetic field by theta eta. Or in other words, in the magnetic field equation, you will get a minus theta eta inside the phase. Okay, now that significance of sigma by omega epsilon. The ratio of the magnitude of conduction current to the displacement current in a lossy medium is sigma by omega epsilon. Okay, and what we are doing here is just substituting for sigma, substituting for omega epsilon. When you do that, okay, what are you going to get? So we will call this as tan of theta. We will call this as tan of theta, okay, where this tan theta is called the loss tangent. It's a measure of the loss. It is called the loss tangent. And this theta is called the loss angle. In case you don't know how I arrived at this equation, I've just put this for you. Just look at this. Y is J ds J omega epsilon es. I've just done it out here for you. And similarly, this comes from Ohm's law. Okay, just substitute and you will get sigma by omega epsilon. We call this as tan theta, where tan theta is called the loss tangent and this angle theta is called the loss angle. Now, look at this last two sentences written here. When I defined the 4 types of medium at the beginning of this chapter, I had said one thing. When the material is a perfect dielectric, or a lossless dielectric, we have seen that sigma is much less than omega epsilon. I had written one condition there. Now you will understand why that condition was written. So if it's a perfect dielectric, what happens is, okay, just please guys, just bear with me. I have to go on the slide. Bear with me. I have to go to the, now look at my alpha expression. Look at this alpha expression. What happens when sigma is 0? In a pure dielectric, lossless dielectric, what will happen? Sigma will become equal to 0. When sigma becomes 0, what will happen? You get 1 plus minus 1. So you get alpha itself becomes 0. What is the meaning of alpha becoming 0? Mahendra Reddy, what is the meaning of alpha being 0? Alpha being 0 means no loss, lossless. Okay, that is why we wrote this condition. At the beginning of this chapter, we had written the conditions like this. Remember these 4 conditions that we had written? When we wrote the constitutive parameters, along with the constitutive parameters, we wrote sigma much less than omega epsilon for lossless, and sigma much greater than omega epsilon for a perfect conductor. So this condition is coming from there. Okay, now let me go and show you that again. Show that again. So when it is a perfect dielectric, sigma is 0. Sigma has to be no conduction. So sigma will be almost 0. So the loss tangent will be very small. Tan of 0 almost. Therefore, tan theta will be very small. Whereas if it is a perfect conductor, it will be the opposite. When it is a perfect conductor, what will happen? Sigma is going to be much greater than omega epsilon. Okay. And in that case, tan theta will be large. Tan theta will be large. Whereas for perfect dielectric, tan theta will be small. Now let us look at this figure here. Come to this figure. Here on the x-axis, you are having your conduction current density. On the y-axis, you have your displacement current density. I have told you in the past also, for a conductor, displacement current is almost 0. So let us consider a conductor. So for a good conductor, the y-axis will be almost 0. So what will happen to this theta? And this theta is always measured with respect to the y-axis. It is measured with respect to the displacement vector. Okay, so when you measure this for a good conductor, what will happen is theta is large. For a good conductor, theta will be large. Okay, sigma will be large. Therefore, sigma by omega epsilon will be large. Whereas when you come to a perfect dielectric, what will happen? For a perfect dielectric, this part will become small. Whereas the displacement current will be large. So your graph will look like this. Will be like this. Okay. Or the loss tangent will be very small. And if it's a perfect dielectric, what will happen? Perfect dielectric, what will happen? Theta will be almost 0. So all the conduction is going to happen because of the displacement current. Only displacement current will be there. There is no conduction. Whereas for a pure conductor, what will happen? This y-axis is not going to be there. Only the x-axis will be there. Or theta will be 90 degrees, close to 90 degrees. Or tan theta will be large. Though we call it the loss angle, we call it the loss tangent, etc. Remember, for a perfect dielectric, loss tangent will be small, and for a perfect conductor, loss tangent will be large. But we are looking at lossy dielectrics. We are looking at lossy dielectrics. Lossy dielectrics, therefore, it will be somewhere between the two. Okay, so tan theta will not be small, it will not be large, it will be between the two, or in other words, sigma by omega epsilon is not negligible. Sigma for a lossy material, for a lossy material, for a lossy dielectric, okay, sigma by omega epsilon is not negligible. But it is not too big also. It's not big like a conductor. It is not 0 like a perfect dielectric. It is lossy. So it will be between the two. Okay, now I hope you got the physical significance of this sigma by omega epsilon. Okay, now the parameters that describe the behavior of a wave in a medium are the constitutive parameters. And in addition, the frequency of operation. What is frequency of operation? Omega. Okay, so as a result, what will happen is how a medium can be perceived as a conductor or a dielectric depends on the frequency of the wave. A medium which is a good conductor at low frequency can be a dielectric at high frequency. Okay, so how you define this is something that you have not studied in physics. Okay, when you're talking about AC signal, this becomes significant. So whether something is a conductor or not depends on the frequency also. So at low frequency, a material, a medium may be a good conductor. But when you go to high frequency, the same material will behave like a dielectric. I know a lot has been told to you. And again, maybe I'll just only finish one more sentence for you. Few minutes back, when I talked about theta eta, I wrote an equation. There I wrote tan of 2 theta eta is sigma by omega epsilon. And just now we talked about loss angle or loss tangent and wrote it as sigma by omega epsilon. So shut up. Yeah. So what happens is I just want to finish today's class with equation 15. So what is equation 15? The intrinsic, twice of intrinsic angle is equal to loss angle. If loss angle is 30 degrees, then intrinsic angle will be 15 degrees. Okay, the rest we will see in the next class. I know, okay, now the rest of, okay, today's class is also tough. After this, it will not be tough, it will become easy. Anybody wants to say something about today's class? What is the summary of today's class? Anyone? Karthik. Can you summarize today's class? Okay, you cannot, I will do it. When a wave travels through a lossy medium, there will be an attenuation, or exponentially the electric field and the magnetic field will decrease. And that value is going to be dependent by e to the power of minus alpha z. That alpha is called the attenuation constant. Greater the attenuation, faster will be the fall. So that is one thing. Next thing you have seen is that the electric field and the magnetic field, which are perpendicular to each other, okay, they will also have a phase difference between them. The phase difference between them is theta eta. Always the electric field will be leading. Therefore, the magnetic field equation will have minus theta eta inside the phase. Okay, so that's one of the conclusion. Next thing we have seen is what is the significance of what is alpha, what is the significance of the intrinsic impedance. Intrinsic impedance is having a real part, it has got a complex part, and then we introduced the term called loss tangent, loss angle, and we saw the relationship between loss tangent and loss angle. We saw one is twice the other. Then we saw the graph between the conduction current density and the displacement current density. We see that the displacement current density will dominate for dielectrics. And for a pure dielectric, completely it is displacement. Whereas for a pure conductor, it is completely conduction. So this theta is going to depend on what is the material, or the loss angle will depend on the material. Better the conductor, larger will be the loss angle. For a pure dielectric, loss angle will be 0. If loss angle is 0, immediately you can say that intrinsic angle also will be equal to, impedance angle also will be equal to 0 for a pure dielectric. But of course, today we have not talked about a pure dielectric. I know this part of the portion is tough. Please read and come. Otherwise, next class you are not going to understand even a single line. Anything you want to tell me? I've been using different colors and all so that somewhere you can see some patterns and all that. For that only I'm doing this. And important equations I'm putting them in boxes. Girls, anyone has to say something? And missing this class is going to be a suicide. Let me tell you now itself. It's going to be suicidal if you're going to miss this class, because the exams are going to be like your normal classes only. It will be a descriptive examination, please. You have to work out problems, you have to answer.
Ma'am, and the exam is not on the 17th, it's on the 24th.
24th, okay, we have some more time. And next week, fully I'll solve problems. Next week, 1 week, I'm going to solve only problems. Let us finish off the theory in tomorrow's class. Once I finish off this theory, then we will do problems. And when we do problems again and again, the concept also will become clearer. What is now not very clear will become clearer when we solve problem. Because Maxwell's equations also, when I just did the theory, it was not clear. But when we kept doing the problem, you started feeling at ease. Same thing will happen here also. But
Yes,
please study and come.
Yes, ma'am.
I can't do better than this, please. Let me be very frank. Any doubts?